Hello everyone and welcome. In our computing lesson today, we're going to be looking at conversion of number systems. So we'll be looking at binary to denary conversion, denary to binary conversion, and also we'll look at hexadecimal to denary and to binary conversion. Now, in the first example we have here, we are going to convert an 8-bit binary number 1011 to denary. To do this, now there are different ways you can do this, but over the years I have found that most students will go on to complete it in the way I'm about to. Now, just if you try and remember this very common basic rule, so we know that the least significant bit here, so this value here, we know is equivalent to 2 to the power 0, and we know that the next value there is 2 to the power 1, and this value there is 2 to the power 2, and it goes up that way. This value there is 2 to the power 4. You don't want to remember that, but what you should remember is that 2 to the power 0 is going to give us 1, and then 2 to the power 1 is going to give us 2, and I'm going to stop using 2 to the powers now. I'm just going to double the numbers each time. So I've got 1, 2, the next number I will have there is 4, the next number is 8, then I have 16, then I have 32, 64, 128. I'll stop in 128 because I'm working with just 8-bit numbers. And the next thing I want to do is just write down all the numbers I have there. So I have 1, 0, 1, 1, 0, 0, 0, 1. And if I do this, I will then take all the numbers there that have a 1 underneath it. So in this case, I have 128 plus, I won't take that, then I'll take 32 because it's got 1 underneath it. I'll take 16. I won't take 8, 4 or 2. I'll leave those ones because they've all got zeros, and then I'll take 1. If I add all of these together, this should give us 177. And if I want to write it in its purest form, I'll put it to base 10. So 1 not 1 1 not 1 in binary is 177 in denary. Another example is, so second example, let's say we're asked to convert not 1 1 not 1 1 not, another number to base 2, and we're asked to convert this number to base 10. Now what I can do here is you don't have to repeat this each time. Some students would write this once and then just have the binary numbers repeated underneath each value, each calculation, for each calculation they're about to perform. But just for the sake of clarity, I'm going to write it down again. So I'm going to put 1. Again, remember, I'm just repeating the values. 2. I'm doubling the values each time. So I've got 1, 2, 4, 8, doubles each time to 16, 32, 64, and 128. And remember what I've said, that the next thing you need to do is to write down all the values underneath it. So I have 0, 1, 1, 0, 0, 1, 1, 0. Okay. Now, what we've then gone on to do is to add all the values up that have a 1 underneath them. So you see here I have 64 plus 32 plus 4 plus 2. And if I add all of these numbers together, I should have 102 to base 10. Now, one thing I ask students to look out for is, if you pay close attention here, you would notice that this binary number here ends with 0. So the least significant bit of this binary number here is 0. And the value, the denary number we got there is 102, which is an even number. So one way you can easily check for error is to just check if you have a 1, if your binary number there ends with a 1, then your denary should be an odd number. If it's an even number, then you know your answer is definitely wrong. The same thing applies here. If the binary number is 0, and the least significant bit is 0, then the answer you should get must be an even number. If it's not an even number, then you know you've done something wrong in your calculation. It's one quick way to check. The next thing we're going to look at is converting denary to binary. So let's say we have been asked to convert 149 in denary to binary. Now, in the exams, you may be told actually how many bits it's required to store a value. But if I look at here, where I have 149, I know that 149 is not more than 255, and what this means is that it should fit perfectly into 8 bits. So because I know it's going to fit very fine into 8 bits, I'll repeat those same numbers we have when writing our 8-bit value. So 1, 2, 4, 8, and again each number doubling up each time. So because we have this now, the next thing I'm going to check is 149 greater than or equal to 128? It is. If it is, I'm going to put 1 there, and then I'm going to say 149. I'm going to say here 149 minus 128. Now this will give me 21. Okay, so is 29 bigger than or equal to 64? No, it's not, so I'll put a 0 there. Is 21 bigger than or equal to 32? No, it's not, 0, and I'll move on. Is 21 bigger than or equal to 16? It is bigger than, so I'll put a 1 there. Okay, and then I'll say 21 minus 16, and that should give me 5. So it's 5 bigger than or equal to 8? No, it's not. I'll put a 0 there. Is 5 bigger than or equal to 4? Yes, it is. So I'll put a 1 there. I'll say 5 minus 4, which gives me 1. Is 1 bigger than or equal to 2? No, it's not. So I'll put a 0 there. And it's 1 bigger than or equal to 1? Yes, it is. And if I want to just do this, I'll say 1 minus 1, which gives me 0, so there's nothing else to work with. You can see here that we have the binary representation here. So 149 in base 10 is equal to 100100101 to base 2. Another example. Let's look at another example. Let's look at the number. Let's look at the number 204. So if we're asked to convert 204 in denary to binary, again I'll just repeat that same step up here, where I have 1, 2, 4, 8, 16, 32, 64, 128. Now I check again. Is 204 bigger than 100 or equal to 128? The answer is yes. I'll put a 1 there. And I'll just simply say 204 minus 128. And that will give us 76. Okay. Now, is 76 bigger than or equal to 64? It is. So I'll say 76 minus 64, and that gives me 12. 12 is not bigger than or equal to 32, so I'll put a 0 there. It's not bigger than or equal to 16, I'll put a 0 there. The 12 is bigger than 8, so I'll put a 1 there. 12 minus 8 gives me 4. Is 4 bigger than or equal to 4? It is, so I'll put a 1 there. 4 minus 4 gives me 0. It means I'll have all zeros there. So technically speaking, 204 in base 10 is equivalent to 1 1 0 0 1 1 0 0 to base 2. So this is how we convert denary to binary.